So when we're doing the Williamson ether synthesis, we are going to start with we are going to react it with a so NaOH is a base because Na plus. So what do you think can happen when you put alcohol and a base together? So like you have an acid-base reaction. Cool. So the OH is going to take that hydrogen, give the electrons back to the oxygen, and we create the conjugate base of our alcohol. We talked about this a little bit a couple weeks ago. What's the name of the conjugate base of our alcohol? The alkoxide. All right. So now once we have our alkoxide, we are going to introduce an alkyl. Remember, X just stands. And this alkoxide, so I said this a couple weeks ago. Anything with a negative charge is a base or nucleophile. Cool. So I want you to repeat after me. Anything with a negative charge. Whoa, I said repeat after me. This is a whole. But yes, you're right. Anything with a negative charge is a base or a nucleophile. So in this example, it's going to be gonna attack this carbon and kick off our halogen. Yes, anything with a negative charge is going to be base or I definitely can. So once this oxygen attacks this carbon, we kick off. We get a what? Yay! Woohoo! You did a reaction. How do we feel? Two, two. Okay. So anytime you see an alcohol with a base, oxide, if you have an alkyl halide, you are from N. So now we can actually do the reaction intramolecularly. And I'm actually going to go ahead and, because I want to show you. So the premise of an intra is that our alcohol, our leaving group are. And again, I'm going to give you NaOH. So based on the reaction we just yeah, we're going to deprotonate the alcohol, which is an alcohol. We are going to give those electrons. So in the last example that we did, once we had O minus, what did that do? Yeah, it reacted with the alkyl halide. Since the halogen is on the same chain, what do you think? Yeah, it's still going to react the same way, and we're right here. And this is where counting is super, super important. So I'm going to start at the oxygen just because have a 5-membered ring, oxygen inside of it. So I just start at the oxygen to remind myself that the oxygen will be not coming off. But again, that's just like an arbitrary. So let's just make sure we have the right numbers. So we have 1, 5. What substituents do we have? Yes, we have a methyl. Yes, and what carbon is the methyl on? 2 and 5. Awesome. So what did we make? It does look like a curve. But what functional group? Cyclic ether. Again, this is just arbitrary naming. I just did this because I want to remind you that the oxygen is in the ring. But you're right. If we were doing IUPAC naming, we would start with one of the carbons. Yeah. Yeah. We try to do that thing again. Is that better? And we're in 2 minutes. Because I don't want anyone to be like, oh my god, look at that ball. Instead of Cash Money Rose, it's ball of Okay. So now we're the same thing, but with a smaller number of carbons. So you guys already know what to do. What's the first step? Deprotonate. Sweet. So we get bam, bam, bam. Let's say this X is a bromine, just because it's all like bromine, especially magnesium. Anyway, so now what's going to happen? Our alkoxide is going to act as a nucleophile. Cool. And it's going to attack the carbon that has the halogen on it. So we attack off. Now I'm going to start numbering again. Oxygen, just because I feel like it. 1, 2, 3. Oh, it's a tiny ring. Take our tiny ring. So 1, 2, 3. And what are our substituents? Methyl, where? 2 and 3. Cool. Okay. So there is a reason I drew out the stereochemistry. Does anyone want to take? Why would I draw out the stereochemistry? Well, yes. Okay, that's a fact. Yes, we have a cyclic ether. Yeah, because it's going to into a reaction, right? So this guy has to come in from the opposite side, the halogen, and we're off. So it's going to be both. So what I want you guys to remember is that the nucleophile and the lead have to be yes, definitely. So the nucleophile and the leaving group anti to one another, aka have to be in order for this reaction to happen. Wow, this looks the other important thing, the epoxide has to be on one plane, right? So both of these bonds have to be either on the plane, they both have to be wedged, or they both have to be depth. Can't have like one side wedged, one side depth. Yeah, it would be like an SN2. What? Yeah, I mean, it's going to be an SN2 regardless, but you only have to care about that if he gives you wedges. Okay. Yes. Yes, you could. So in this example, it's not like if this was wedged, it's not like the reaction couldn't happen. You would just have to rotate it. But like conceptually, you have to understand that in order for this to happen, they have to be in. So good. All right. So besides cyclic ether, this guy has a special name. Does anyone know what it is? Think about the title of this section. Alcoholic ethers and epoxides. Epoxides, yes. So an epoxide is specifically a three-membered cyclic. So this is where I always have to kind of shove this in your brain. So an epoxide is always an ether, right? But an ether is not necessarily any. Epoxides are just a very, very, very specific. So now that we made cyclic ethers, let's break them because that's what else would we do? So let's say we have this guy, right? How could we break? And what about it? Okay. Ooh, okay. So ethers can only be cleaved in. You said acid or base. That's wrong, actually. So regular ethers can only be cleaved in acid. They're going to be stable in. Exactly. So what does that mean? I will show you. The first, I'm gonna. This is one of my favorite things. There was the magnesium bromide saga, and now we have acids, right? So when we have the order of reactivity for ether cleavage, that's what he's going to say. What does that actually mean, right? So having an acid versus catalyst is going to influence your nucleophile to attack a certain. I'll show you exactly what I mean by that. But the order of reactivity just refers to the order preference. Nucleophilic. So we know that regular ethers can only be cleaved in acid. So in an acid, order of preference is 3, which is tertiary, 2, which is secondary, 1, which is primary. How annoying! It's not in number order. That's because acids are. I only got 2 left. That's. Thank you so much. Okay. So then what the heck does that mean? Let's go over here and let's do this reaction. So on for our starting material, I mean, we have cyclic ether, and we are reacting with HBr, which is it is an acid. Cool. So what do you think could possibly be the we could do a nucleophilic attack exactly, and that is what we're going to do. But something that Dr. West is very passionate about is this first. So the first step is going to be the oxygen sealing the H coming. Call that the. Any idea why we would call it the activation? Yeah, we made it acidic, but you said we're doing a nucleophilic attack, right? Yeah, it's a better electrophile and it's going to be a better leaving group. Cool. So now this carbon, is it primary, secondary, or primary? Yes, because again, this bond doesn't count. What about this carbon right here? You were tricked. It's secondary, this one right here. Because this bond to the oxygen does count. We're only counting bonds to other carbons. So on this side, primary, on this side. So since we had an acid, what was the order of preference? That would be too easy. It's a pain in the ass. So it's what? 3. No. Three, 1, 2. That's why it's a pain in the ass. Yeah, sometimes I think the right. Really poor execution. So the order of preference for an acid is actually 3, 1, 2, and that is why it's a pain in the ass. I have fault. What happened? Yeah, exactly. Now going back here, I'm going to pretend that fiasco didn't just happen. So what's the order of preference for an acid? 3, 1, 2. Spectacular. You guys are... Okay. So this Br minus is going to attack which side? The primary or the secondary? Primary, because primary is better than secondary. So look very carefully, please. We attack the primary side, break this bond, the oxygen opens up that way. So now I'm going to number it. And again, this is just arbitrary numbering. I'm going to start here. 1, 2, 3, 4, 5. I have a 5 carbon chain. 5, 1. What do we have on carbon 1? We just did a nucleophilic attack, right? A BR, yeah. So the nucleophile is going to attach to that primary carbon that's in. Cool. So then what do we have on carbon 5? We do have a methyl group, and we have something else. And oxygen, but is it just an oxygen? So we ended up adding the bromine primary, which opened up no, we're not going to worry about it. Any questions? So the second reaction is like almost exactly the same. So I'm going to copy and paste the first step. Yes, it's going to do the reaction twice because we have excess HBr. So at this point, we have more HBr. What do you think could possibly happen? Yeah, so we're going to protonate this guy. And why would we possibly want to protonate him? Yeah, the water is going to become a better leaving group. Plus, and what's going to do the attacking? Br minus, exactly. So Br comes in, attacks, takes off the leaving group. So we get this lovely new chain. Never give myself enough room to still have this bromine. And now we added an extra bromine out of tad. So if he just gives you 1 mole of R, final product that has. But if he gives you excess, you're going to one more time and you're going to. I don't have any questions specifically. On a scale, we're going to do the hand. 0 is I came in here knowing nothing and I still know nothing. And 5 is wow, I can take the test right now. I feel amazing. How do you guys feel? Yeah, 1 through 5. You pick any number. Okay, you know what?
1 or 5.
Yeah, you get no other choices. No, okay, that's better than a 0, so I'm happy about that. Again, you haven't covered this in lecture, so go to lecture, learn all about it, talk some more on when. Not a tutoring.
What I am?
Oh, you know what, Chris? This from you. Everyone but Chris. Have a wonderful day. See you
I think
later.
it's fantastic.
And then if you didn't sign in, think, oh my god, no. I'm just gonna edit it out.